All right, so it talks about proving angles. So this section deals a lot with just solely looking at certain types of angles and being able to identify them to be congruent. So one on that so much it's very common sense is that if I have two right angles, what can you say about any two right angles? If I gave all of you a right angle and set it in front of you on your desk, what could I do about any two of them? Any two of them are going to be what's one another? I think 180, yeah, but and just comparing their two sizes, they are supplementary, equal, right? Any two right angles, so I don't know if you're saying is right, but any two right angles are going to be the same thing, right? Does that make sense? Is that common sense? Is that almost like, dude, why are you saying that? That's stupid to even take space in a textbook for? But it's something that we will use consistently, okay? Something that is, as I think, almost common sense like in regards to that is this one here, okay? Now, this is what we call a theorem. So a theorem, we use these words like conjecture. A conjecture is just a statement. I'm making a declaration, okay? I'm making this argument, this statement, okay? But a theorem is a conjecture or a statement that you can prove to be true, okay? Postulates we had to assume to be true, right? We could draw pictures and we could justify them that way, but we just had to take everybody's word for it, or take the mathematical fathers' words for them that's true, okay? And everything else was based off them. Theorems can actually be proven. We can actually show why they're true, okay? So when we go through this proof process that we've been trying to kind of introduce the last couple of days, the main reason for doing those proofs is for us to develop the skill for being able to show why these types of things are true, okay? Now, in doing that, when we see other proofs and the proofs that we've already done, they were just arbitrary things. They were just kind of random types of problems, okay? The overall process of a proof, its intention, is to be able to show useful things to be true. Does that make sense? Like the proofs that we did yesterday. So let me pull one of those up real quick. Where did it go? There. So this proof yesterday here, okay? We showed it to be true, but the conclusion that we get from that 1 and 3 are going to be complementary, okay? Or I guess 1 and 2 are going to be complementary. That's not going to be something that we see over and over again throughout this course. We'll probably never see that picture ever again. So even though we went through and we were able to show and validate that that's a legal argument, it is a true statement, that was just more of a practice type problem to get us in the flow of how we understand how we work with proofs. Because then if we can start doing that, we start getting that practice, then we can get to something like this, where we are proving this theorem, and then we're going to see those angles all the time. And it almost gets to a point, guys, where every single one of our questions at some point will incorporate these types of angles at some point. Okay? So that's the idea of what proofs are for, is to prove these useful statements. Okay? Now, as you write this stuff down and you start learning these things, I'm going to tell you not to, and I'm going to present all your theorems because I just cut and paste. I've typed them out and drawn pictures. I cut and paste these out of a textbook. Okay? Your online textbook. So our online textbook calls this theorem 2.1. Okay? But if I go to Elida and get in Elida's geometry class, their textbook might call that 3.1. Okay? If I go to Perry or out on the East, they might have it as 1.1 or 3.2 or 2.2. Does that kind of make sense? Okay? It might come in different places in those textbooks, so we don't ever want to remember it by the number. Okay? There will be a handful of theorems that have special names to them. This one has a special name to it. Okay? Vertical angles theorem. Which basically tells me what we're talking about inside the theorem. But if I just say vertical angles theorem, and I don't read what the theorem says, I have no idea what is being encapsulated in that statement. So I would much rather prefer you guys to learn these things by what they say. Okay? By what they say. So the vertical angles theorem states that vertical angles are congruent. Okay? Now, what I don't like about what this author does is that they spend a great deal of this chapter talking about if-then statements. Would you guys agree with that? And the purpose of them talking about if-then statements is because theorems are if-then statements that are true, that are 100% true. But this one, it's not written, the first one that we come across, they don't use that structure. So we should maybe better write this. If two angles are vertical, then they are congruent. Okay? That's a better way of saying that vertical angles are congruent. It's a little more wordy, right? But it's an if-then statement. Okay? And that's what I want to kind of reiterate to you guys is that every single theorem that we come across this year is an if-then statement. And that's why we spend so much time talking about how we read if-then statements and what they mean to us. And here's the idea. If you start with two angles in front of you that are vertical, you can now make the jump, the conclusion, that they're equal to one another. Their measurements are the same. Okay? Well, what you need to understand, and this is what people want to do, well, that means if vertical angles are congruent, that must mean congruent angles are vertical. They want to flip it. But we've talked about how making the converse does not always produce a true statement, right? If I say in front of you, you have two angles that are congruent, does that mean they have to be vertical? No. Okay? So in a textbook, okay, when we're going through our notes, and there is a theorem that's written as if-then, they're telling you that is the only way that you can apply that logic. That is the only way that you can use this conclusion or arrive at this conclusion, is if you start with the if part, you can then get to the conclusion in that order. Does that make sense to everybody? And you'll want to, and I'm the same way, but inherently you'll want to be able to flip things back and forth. Okay? But if it's stated as if-then, you can only do it that way. Okay? So I want to prove this. This is actually a pretty easy thing to prove. Okay? And I've got some stuff here that I copied out of the textbook. And again, I don't like what this author does here. And I'm not going to make you do this, but I'm going to, at this stage, add some statements. All right, so what we want to do, I'm going to talk about the given here and the proven, how they generate those, okay? The theorem said if two angles are vertical, then they are congruent. And I told you, if I'm going to prove a theorem, the if part becomes your given, right? Okay? Well, I don't want to write my given that just says two angles that are two angles that are vertical, okay? Because then I don't know how to talk about the first angle or the second angle. So we give specific names to them. All right, so angle 1 and angle 3, would you agree that those are still two angles? Is it stating in that statement that they're vertical? So that statement there, that phrase right there, aligns itself with exactly what we said right there. Two angles are vertical. We just need, in a proof, specific things to talk about. So we name them as 1 and 3. The conclusion said, then they are congruent. Is that what this conclusion here, or this proof is saying? The two angles that we define here are congruent. Okay? So when we do these types of things, when we take a theorem and we rewrite it so that we can actually prove it, we won't rewrite it verbatim. We won't rewrite it word for word. We will introduce specifics so that we can talk about them. Okay? We'll give names to those two angles, or give names to whatever objects the theorem is talking about. Okay? So statement 1 here just simply says, write down your given. Okay? So statement 1 is your given, then your reason that obviously that was given. Okay? So we know we're starting with two vertical angles in front of us. Okay? Now, this is one situation that kind of contradicts those 7 steps I gave you the other day. This is going to be one of the only times that it does this. There's a vocabulary word there. Vertical angles is a vocabulary word, right? And eventually, we will use that vocabulary word to generate congruency, okay? But vertical angle, you will never, ever, on the right-hand side, ever say that it's the definition of vertical angles. The definition of vertical angles just provides us a way of how they're created, okay? How they exist. And that doesn't give us any real useful information, okay? I'm going to skip over that vocabulary word in this problem. Does that make sense? Okay. When we prove a theorem, here's the thing, and it's much like how we define words. We talked the other day about the word endangered. If I was going to define the word endangered, would it be good or bad to say endangered means that animals are endangered? Or if I were to define endangered animals, and my definition is that they are animals that are endangered. Does that really give me a good idea of what that definition is? No, I can't use the word that I'm defining inside its definition. That doesn't make, it gets you in what we call an infinite loop in computer sciences. You get stuck into something, you can't get out of it, okay? Because you don't know what endangered means, so you look it up, and it gives you a phrase that uses the word endangered. And then you look up endangered, and then you get back into that loop. Does that make sense? Okay? It's called an infinite loop. That's a problem. Theorems are the same way. You cannot prove a theorem using that theorem. Okay? Because proving statements is using previously known facts, right? Well, this is not a fact yet until we're able to demonstrate that it's true. Okay, so we don't know this is true until we get down to statement number 6. So if you're trying to prove that 2 angles that are vertical, if they are vertical, that they're congruent, you can't use that statement inside this theorem. It'd be like defining a word using that word. Okay? Just got to keep that in mind. Whenever we come across a theorem, we can use everything prior that we've learned throughout the year. Okay? I think it's important to kind of go through those steps that we talked about yesterday and the day before. We get to the point where we exhaust all our vocabulary. And I said we're not going to talk about vertical angles. So we get to our vocabulary, we can't do anything, but then we can look at our picture eventually. And this is why I added this stuff here. Would you guys agree that those 2 angles right there are a linear pair? So I think it's important to say that they're a linear pair here. Would you agree then that these 2 angles are also a linear pair? So I think that's kind of why I try to jam that in there between statements 1 and 2. Because I think before I tell everybody that 1 and 2 are supplementary, I have to tell them they're a linear pair. How do I know they're supplementary? Well, it's because they're a linear pair. Does that make sense? And I think the author takes some liberties here, which are not, I think, wise to do. Once I say they're linear pairs, then, because we know we had a statement that said if 2 angles are a linear pair, then they are supplementary, right? So once I say they're linear pairs, I can make the argument that they're supplementary. If you remember, that's the linear pair postulate. Okay? Every single time that you make the argument that 2 sets of angles are supplementary because you looked at a picture and the picture told you that, your reason will be linear pair postulate. Okay? Now, everything else is consistent with the way that we should do this proof. Okay? Once we have the fact that in statement number 2, 1 and 2 are supplementary, what does supplementary mean to us? These 2 angles are going to do what? 1 and 2 are supplementary. They're going to add to 180, right? Okay, so that 1 plus 2 equals 180 is based off of knowing that we were able to classify the angles as supplementary. Okay, so that's the idea that we introduced a vocabulary word. We introduced supplementary here. So then we have to tell everybody, well, what does that mean for our specific problem? It means for us that 1 plus 2 is 180. But didn't we also introduce a vocabulary word right there? We introduced supplementary a second time, right? So then it makes sense to write down what it means for those 2 specific angles, 2 and 3. Does that make sense to everybody? So I know they're supplementary. because they were a linear pair. Okay? Now I know it adds up to 180 because I know what it means to be supplementary, right? And I know what it means to be supplementary because it's encapsulated in the definition of supplementary angles. Does that make sense? The next step is not as obvious as I think that step. Okay? What we find out, at least in my opinion, is that if we can make comparisons to what we've already done in algebra, it makes proofs a little bit easier. You guys remember last year, if I gave you this line, or whoever your math teacher was, gave you that line right there, and they gave you this line right here, and they asked you to find out where they cross. You guys remember the first day of that work, you would graph both of them, and then just kind of see what the ordered pair was, where they cross? You remember doing that? Do you remember the next day, you were shown an algebraic process that basically said take that and set them equal to each other? And when you solve that equation, the x value in that equation is the x value of where the lines crossed the day before. Remember doing that? You guys know why you can do that? Why you can take this expression and set it equal to that expression, solve it, and it gives you the answer of where these two things cross? The y, the WHY, you can do that is because of those y's. What are those y's to one another? They're equal. They're the same thing, are they not? If those two things are the same thing, then the blue things have to be the same thing. At that point, algebraically, at that point, x comma y. Okay? Does that make sense to everybody? If two lines are going to intersect, then they're going to share the same x value, and they're going to share the same y value. So the argument was, well, if these y values are going to be the same, then the expressions that generate them have to be the same. So look over here at this stuff. Would you guys agree that that 180 right there is the same as that 180? Does that make sense? So if the 180s are the same, can't we make the argument that the ideas or the sums that generate those 180s, those two things have to be the same? Does that make sense to everybody? So statement number 4 is taking statement number 3 and saying measure of angle 1 plus measure of angle 2 is then equal to measure of angle 2 plus measure of angle 3 because they both were equal to 180 earlier. Do you guys remember what this process was called in Algebra 1? There were two processes that you went through that told you how to find where two lines crossed. One of them was called elimination. You remember hearing that word? Okay. The other one was substitution. Okay. That's the reason why it's called substitution is because you replaced this idea with two things that they were equal to. That's what we did here. This is substitution again. So my hope is kind of drawing that kind of link between what we did last year algebraically can help you recognize that when I have two things in a proof that are equal to one another, I got those 180s. 180 is equal to 180 all the time. Then the things that generate the 180 on the left-hand side should be equal to one another as well. Now, why is that useful? Look at that statement number 4. And they highlight it here. Okay? And remember, what this means is you got a number plus a number is then equal to a number plus another number, right? But what do you recognize about those two numbers? They're the same symbol, right? And if they're the same symbol, it means they have to be the same number, whatever that number is. Well, if I have the same amount on both sides, can I remove that amount from both sides and still end up with a true statement? So all they do here to get from line 4 to line 5 is they get rid of that thing. They get rid of measure of angle 2. And you can see all you'd be left with is 1 and 3, right? When you remove something from both sides of an equation, what are you actually doing? What operation? subtraction property equality, right? Okay. So now I have a measure of angle 1. So I know I'm talking about an angle, right? Its measurement's the same as the measure of angle 3, another angle. So if I have two angles whose measurements are the same, doesn't that allow us to jump to the conclusion that the two angles are congruent? If you remember from yesterday, if we go from equality to congruency or congruency to equality, that region will always be the definition of congruency. And if you think about what we just did, we started off with the statement that angle 1 and 3 in our picture were vertical angles. And we go through a series of steps that are true. We know those are facts. Each individual statement is a fact. And we, at the end, spit out with something new. 1 and 3 are congruent, which is now a fact that we're going to use endlessly throughout the rest of the year. Okay? But that's the idea when you come across a theorem, and we'll see. I don't have the physical textbook, but if we were to go back to the textbook, every chapter has anywhere between 10 and 30 theorems in them. Okay? And they're just statements that are true that we're going to use over and over and over and over again. Okay? So now in the next proof, and we'll see this on Monday, the next proof that we use or that we conduct, it will have vertical angles in it. And we'll have to use those vertical angles being congruent somehow. Instead of showing all 6 of these steps in that proof, we'll use this theorem and say, well, we know because we've already proven it to be true. And whenever I see vertical angles are going to be congruent. Okay, so we'll talk about that again on Monday. But what's the benefit of this? When we start seeing questions like this, okay, we learn theorems, and then we'll see these algebraic problems that people are more fans of than the theorem process that practice our understanding of that theorem. So what are you going to say about 3x and 2x plus 40? Okay, they're vertical angles, so if they're vertical angles, then they're congruent, right? So their measurements have to be equal. So you see how it develops a relationship? And what I mean by a relationship, it develops an equation here, right? I can relate 3x to 2x plus 40. And I'll let you solve that stuff, but that's using that idea that vertical angles are always going to be congruent. What about that one there? What am I going to write there for that expression, for that picture? I'm going to say 2x plus 21 equals 4x. All right, so as we go through the year, guys, we're going to find out you guys passed Algebra 1. So I'm going to make the assumption that we can solve 2-step, 3-step equations. I want to get to one like this real quick before the bell rings. We got a lot of things going on here, right? Okay? You have a lot of relationships in this picture. Okay? What jumps off the page to most people, I think, because we've used it the most so far, is this. That angle and that angle. Does anybody see a relationship between those? Can I say 3x plus 8 plus 5x plus 4y equals 180? If I start combining like terms, I get 8x plus 4y equals 172. Does anybody know how I solve that equation? I've already said the word today once when we start talking about substitution. You guys remember the elimination technique? If you have an equation that has two variables, you need another equation that has the exact same two variables. So I need to look at these two angles. Do you agree that those two angles are supplementary as well? Will that give me 10x plus 4y eventually equals 200? If I add those two angles together, so I'm equal 180. You guys remember lining those things up and eliminating the y's in this case? And that's a tedious process, right? You guys agree that's a pretty long thing to do? But if we're intelligent about our picture and we don't just start rambling through and doing something, but we think about our options, what do we recognize right here with the blue angles? They're vertical, right? So that relationship has to exist and has to be true as well. Would you agree that that equation is a lot easier to solve because it only has one variable? If you solve either of those, you're going to get x to be 14. Okay? But it's so much quicker to answer with 3x plus 8 equals 5x minus 20. As we go through the year, okay, you're going to see that there's going to be problems that we might have one problem that we could probably do 60 different ways. There's always a way that's most efficient, though, right? I would not want it on the ATT, 60 questions in 60 minutes. I wouldn't want to use a system here. I would want to make sure I use the relationship of vertical angles. On a test over this information, I would maybe want to use vertical angles so I don't waste time and not finish that test. Tomorrow, I won't give you one this difficult, but I'll give you a question tomorrow about vertical angles like this one or like that one, just to demonstrate whether you kind of all on the same page with what we talked about today. Okay? Most of the tests, though, like I said, would be sections 2.1 through 2.5. And if you think about those, about all of those was a lot of like procedural stuff and how to write and read things, okay? And understand truth value of things. There will be vocabulary as well. All right, so give that optional review a shot. Okay, work on that. And then if we're delayed tomorrow for any reason, we will still have a test. I'll just shorten it. Okay, that's kind of how I deal with delays, unless it's a 3-hour delay, and then we won't do anything. But